So next up, we have Dr. Helena Deus. She received her PhD in bioinformatics from Lisbon University, where she focused on linked data and semantic web applications for healthcare and life sciences, with an emphasis on cancer research. Helena is passionate about applying data science to improving healthcare, in particular for oncology. She works for Elsevier as Technology Research Director and is leading the effort to build a knowledge graph for health. Prior to joining Elsevier, Dr. Deus's role included directing a data science team at Foundation Medicine and leading the healthcare and life sciences strategy at the Digital Enterprise Research Institute. Dr. Deus has published over 30 peer-reviewed papers and was one of the winners of the Big Data Track in the 2013 Semantic Web Challenge and one of the Linked Data Cup with her work on linking data from the Cancer Genome Atlas. Welcome.
Thank you, Heather. Wow, Dr. Deus makes me sound so formal. So, let's talk about deep learning. So Heather asked me to talk about machine learning and deep learning, but I do want to emphasize that my passion is in healthcare. I actually am very much of a nerd, and I started my programming days on one of these devices. Who had one of these devices growing up? Right? So for a lot of us, this was the only computer we had access to. So I would actually go to that program item and program this calculator in BASIC using that tiny keyboard that they gave us. It was fun. In the meanwhile, I graduated to MATLAB. This was my first few years of my career. I was using MATLAB mostly for statistics and modeling, a little bit of machine learning. But then, you know what I realized? That we can't do anything without data, without cleaning the data, without having access to the data. And so my journey toward PHP and JS began. Nowadays, I'm more on the Python side because you can do what I was doing with PHP and Node.js in Python anyway. So that's all I use nowadays. But besides being a nerd, as I pointed out, I'm very much passionate about solving problems in healthcare. Most of my career has been in healthcare. I strongly believe that deep learning, what we now call AI, which is 90% of it is deep learning, can have a huge impact in particularly cancer care. And the reason why I am not going to stop pursuing this is because my sister was diagnosed with leukemia when I was young, and unfortunately she passed away. So I really strongly believe that deep learning will help us prevent situations like what happened to my family. So let's talk a little bit about rules. As a society, we work with rules. We learn to live as a society by agreeing on rules, right? Rules about how to farm, rules about who's going to help with the crop. We have developed also financial rules, right? Rules that prevent certain organizations from taking advantage of vulnerable people. We have rules of architecture, rules about how to build a house, how to build a building so that it doesn't fall down, what materials to use. These are all rules we've learned by trial and error. There are traffic rules as well. You know, before cars became pervasive, there were no traffic rules per se. Maybe, you know, there were some rules about how to, you know, how your carriage should behave. But, you know, traffic rules became really important when we started having a lot of cars on the road. So these all were learned by society through trial and error. Some of them make sense, yes. Some of them were just, you know, people decided to agree on those rules because bad things were happening and they had to come up with rules to prevent those bad things from happening. Machines learn rules too. And this is the key concept, the key idea behind deep learning. Who here has used deep learning to play around or do some exercise? All right, so I'd say 50-50. When you feed a bunch of images of dogs and images of cats into a deep learning network, what it will learn is what number to multiply each pixel by in order to learn how to classify that image. So your training set is generally a very large set of groups of images, and 50% of them, hopefully, are labeled dog, 50% of them are labeled cat. And through iteration, trial and error, the algorithm will try to learn the weights or the numbers that it needs to multiply by each of the pixels in order to correctly classify that image. And if your model has been properly trained, once that training is done, you can give it an image of an animal, a dog or a cat in this case, and it will correctly predict the correct label. Now, this is how self-driving cars work as well. The big difference here is that when you're training a self-driving car, when you're building the data set to train a self-driving car, you need to train it to recognize the events that are happening very, very rarely. So a car has to be able to distinguish between a plastic bag and a baby, because it's okay to go over a plastic bag. It's not okay to go over a baby on the road. So hopefully this part is not going to be too patronizing, and a lot of you understand the concept behind deep learning, but I'm very visual. So I'm not going to show you math, I'm going to show you diagrams. So this is the cool part about deep learning. Say you have 3 friends, you're A, you have friends B, C, and D, and you're giving them a piece of information. And then they are then going to be giving a piece of information to E, and then E has to decide on a solution that based on the information that they're getting through the network. So let's say that you're trying to get E to guess that what you're holding in your hand is a purple hat. The way linear algebra works, the way deep learning works, is you start by assigning random weights of how much strength, how much information each of your 3 friends, B, C, and D, will get. And that's what's represented here. So A is connected to B, C, and D, but A is not connected to E. So there's no weight associated with that last row, right? So this is when you multiply that. Now you're going to have 20 bits of information, let's say, which is your purple hat. Those 20 bits of information are represented as a vector, which is now going to be multiplied by the matrix. And you get a result, right? I'm sure most of you learned how to do this matrix by vector multiplication in school, so I'm not going to go over it. But at the end of that math, what you get is B, C, and D now, each one of them has a little piece of information, right? Because of the nature of the weights, initially, B will have a little bit more information than C and D. Those weights had been organized randomly. And now you've got a new matrix, right? So now B, C, and D are on. They're the nodes in the network that are active. A and E are inactive. So this is why you have 3 ones on the last row, right? So E is going to receive information from all 3. And then again, we know that the number of bits that each node in the network has comes from the previous vector, right? So now, again, you multiply this vector by this matrix, and you get a new result, right? So now your 20 bits are all on E. But are they the right 20 bits, is the question, right? So let's say that based on those 20 bits, E suggests a brown hat, right? And it asks A. Was it a brown hat? Were you trying to tell me about a brown hat? And A says, nope, that's wrong. And says, but you're not too far off from your target. And from 0 to 1, your distance from the target is 0.6. And so E goes like, okay, I don't know who I'm going to blame for this, but I'm going to just distribute my error backward through the network, right? So this is what in deep learning is called, well, in machine learning is called backpropagation. So the knowledge you gain at the end of the network is going to be propagated toward the beginning of the network. And this is the process of trial and error. Based on this, the network will learn the appropriate weights, right? These steps are repeated again and again and again. And I want to show you this. This is a cool demo. So imagine that you've got 3 classes, right? A green, a purple, and a yellow. And this is what a neural network will do. The neural network will literally transform space. So once the information gets to your friend E, it's kind of like all rumpled up together like that, right? And this is what E gets. E has no idea how to kind of turn that back into the 3 classes that made it up. So what the network will do, it will literally transform space so that it'll start by lifting this little piece, and it'll ask, did I get closer to being able to separate these 3 pieces of paper into their individual classes? If I did, then I'm going to keep it, and I'm going to keep moving in that direction, right? And so it will keep doing that. It will keep transforming space until you get your 3 classes back, right? And as it did this, it has memorized the weights that are necessary to transform space in order to get those 3 classes back. That's literally what the neural network is doing, nothing else. It's the principle of deep learning is as simple as that. You're transforming space, you're applying linear transformations to space until you've learned the weights that are necessary to produce the output that you're looking for. If you're thinking it's too complicated to implement this, it really isn't. We're in 2019, and there are at least 3 frameworks that I know of where you can build a deep neural network and train it in less than 10 lines of code. My favorite is Keras, but there are others. There's PyTorch as well, and TensorFlow just came up with a very similar, very Keras-like model abstraction that lets you train a neural network very easily. The last piece I'm going to talk to you about, because it's very cool, is when you start getting deeper into neural nets, you start realizing that you may need to play around with the gradient descent. And what is the gradient descent? Imagine that you're in a mountain. You're in the mountain peak, and your one objective is to go down that mountain, right? So this is how the neural network decides which direction it should change the weights, which of the linear transformations it needs to do in order to get to the right result. So at every point in time, if you're standing in a mountain, you can feel the gradient, right? You can feel whether you're going down or you're going up, right? So the objective here is to always go down, right? So you keep going down, and if there is still a ways to go, if you can still go down, you'll keep going down, right? And occasionally you get to a local optimum, right? You'll notice that there's a deeper well on this chart. It means you can go deeper, meaning you can get better at your prediction, right? And so this is a problem that you'll face a lot when you're doing deep learning. You'll fall into this local optima, right? So that's why it's important to figure out some way to kind of like shake your graph a little bit. Maybe you need to go up a little bit in order to then go back down to the deeper hole. And so these are all the things that you end up spending your time doing when you're applying deep learning. But they can still go wrong, right? I'm sure a few of you have seen some examples like this, and I have to hurry up but essentially, somebody took one of these image recognition neural networks, and they pushed a bunch of muffins through, and it actually said, oh, that's a brown and white teddy bear, right? The second one, that's a close-up of a stuffed animal. So neural networks can be fooled. And another one that I found. So here's the reason why it's so important to know that neural networks can be fooled, is because they are now being used to make decisions on lending practices. Banks are actually using these to decide whether they should give you a loan to buy a house or not. IBM just announced they can detect with 95% accuracy who's going to quit their jobs, right? But what if they're quitting for a perfectly reasonable explanation, right? What if they want to spend the rest of their lives taking care of their kids, right? I mean, you shouldn't be preventing your employees from leaving the company if they actually want to do it, if they have, good reason to leave. And this is another one that worries me a lot. I mean, every week I find these AI-biased examples, and it breaks my heart that we're actually going in this direction, and very few people know about this. So things you can do, right? I can't finish without telling you about some of the things you can actually do to avoid this. If you're put in a position of building a deep learning network, or a neural network, and you're being asked to do predictions on some data, here's a few things you should do. Demand to see the training data, always. So ask yourself, if you're being asked to give some accuracy on some numbers, is your data set balanced? If you're trying to separate dogs from cats, do you have a 50-50 data set? If you don't, you need to break your data set. You need to throw away some data if necessary so that your data set is a 50-50. How is your distribution, right? The distribution of pixels in images is very important. Are the images that are being used to get predictions from your neural network, are they in the same range of distribution as the pixels of the images in which it was trained, right? So that would be one way to avoid that muffin to dog prediction. Generalizable, right? We have this terrible tendency of overgeneralize on the models. So that IBM predictive model, what type of employees were they using in their training set, right? Were they all males? Probably they were, or males were probably very overrepresented on that data set. So you really can't generalize in most cases to, employees across the world. Another one that for me, it's the biggest pet peeve. Pathology, neural networks are being used to help pathologists detect cancer, but they're mostly being applied on this one data set that was made available a few years ago called Chameleon. It was only breast cancer and only lymph node. And people are taking these models, taking images from some other tissue types and going like, oh, yep, there's cancer. Here's the thing, the neural network will always try to do something, right? It'll try to predict something. It doesn't necessarily mean it's right. Because if it's not being used on the type of data that it was trained, it's going to be completely off from what it actually is. So more things you could do. Lime. Lime is a tool that it's one of the tools that I use. It essentially, once you're done with the prediction, Lime will tell you, yes, this is what I think your model did in order to come up with that decision, right? So in this case, the food is being classified as poisonous, and Lime will tell you, oh, it's because of this property that it's being classified as poisonous. Essentially, this property is the one that's most influential to make that classification. Attention, right? People love to say that deep learning is a black box. It really isn't if you're using it correctly. So you can ask each of the layers, what is it that is being outputted? What is it that's being activated in the next layer? And this is just a fun GIF or GIF. Finally, try to break it, right? The scientists at MIT did this experiment, right? They took a pretty good classifier that was able to classify a gazelle based on that image, and they just threw a bunch of noise at it, right? They tweaked the pixels a little bit, and now suddenly it's classifying the gazelle as a tree. Right? So they were actually able to fool the neural network with a little bit of noise. A human being wouldn't make that mistake. It's still a gazelle, even though it's a noisy gazelle. So try to break the neural network, try to break the algorithms to see if they have been trained appropriately and they're being used for the right thing. And at last, I could not have a slide about we're hiring. So if you're looking for a job, you want to do cool stuff with healthcare data and deep learning, my email is up there. Send me an email. Let me know what types of things you'd like to work on. I mean, we're very actively hiring women specifically. We're trying to get to that elusive 50-50 number in technology. It's not easy. So I need your help to get us to that 50-50. But yeah, overall, that's all I wanted to say. All right. All right.
Thank you.
Thank you.